Okay, everybody, welcome to class. I think this works now, kind of. Okay, welcome to class. Happy Friday. We're going to go ahead and get started in class today. First thing we're going to do is wrap up where we left off last time, which was talking about the forces that exist between atoms as you bring them closer together or further apart. We're going to turn that into an energy, and then we can start turning that into all sorts of things that we actually care about, like stiffness, melting point, things that materials properties that we might be interested in. We'll then talk a little about the different bonding types, and we'll actually be able to calculate what fraction of the bond is ionic, or covalent versus ionic bonding. I think we're going to move on to chapter 16 today, and we're going to start talking about free energy. So this big nebulous concept we've been calling energy, we're going to nail it down and start defining what exactly we mean by it. And to do that, we need to describe entropy and enthalpy. Okay, so let's get started. Let's pick up where we left off last time. Last time, we said that every set of atoms that are close to each other, and right now we're just talking about two atoms, right? As they draw close to one another, if there's an anion and a cation, that means that they're negatively and positively charged, that they feel an electrostatic attraction to one another. And we gave you an expression that shows that. Meanwhile, we said if they get too close, that leads to a repulsive force between them. That repulsive force, we call it a hard sphere model, because if you get really close, it takes off. Now, when you add these two together, there's a net force, right? This green line, which is equal to 0 at a certain point, where there's no net force acting on your ions. If there's no net force, they're not going to come closer or further away, they're just going to sit there. But everywhere else, there's some net force acting on them. And the last thing that we said before class ended is we said, hey, you can go from force to energy. These two are related, right? For example, the force is equal to the derivative of energy with respect to R, right? So if we had an expression that described energy as a function of R, we could just take the derivative and we've got force. Now, I gave you force, so we're going to go the other way. We have to take the integral of force with respect to R to get to energy. So if we're going to, basically, the derivative of some function looks like this green line. What does that function look like? Turn to a neighbor and give it your best shot sketching what function, if you took the derivative of it, would give you a shape like that green line, right? A 0, for example, a 0 of the derivative is a max or a min of the other function, right? When this one's negative, that means your function's decreasing. When this one's above 0, positive, it's increasing. So go ahead and try and sketch that with your neighbor real quick.
At the end of class, will you just announce
I'll do one. Okay, does anybody feel brave enough to come and sketch it? Anybody feeling brave this Friday afternoon? Nobody? Everyone's like looking away like, no. Okay. Nobody feeling brave? Okay, let's do it together. If this is the derivative, the green line's the derivative, we're going to sketch it. From 0 up until R0, the derivative is a negative number. That means our function is decreasing. The fact that it's a big negative number means it's decreasing sharply at first, and then it's decreasing less and less until it reaches the 0, where it's going to reach a minimum, right? So let's go ahead and sketch this. We'll do green again. Right? So it's decreasing until it reaches a minimum, and then your function up here, everywhere above R0, it's a positive value. It's going to start out increasing slowly, then hit a maximum value of increasing, and then it's going to just always be increasing, but just barely. So what that looks like is this. Right? Our maximum slope is right here in the middle. I don't know if I made that line up or not, but that's the maximum slope. Otherwise, it's always a positive number. So this is the energy. We're talking about the energy associated with two ions coming close to each other, right? As you change R, what this tells us right off the bat is that there is a minimum energy located at R0. That's another reason why things have a bond distance, right? Because that's where they're in their lowest energy state, right? You can't get any lower than that, okay? Now that said, let's write up some expressions that help us quantify this, right? This is the net energy, right? That's the attractive and repulsive energy put together. So let's write an expression for that. En we're going to say that that's equal to negative A, where A is a constant, divided by R to the M, another constant, plus B, a constant, divided by R to the N. So this is like the most generic way that we can express this. They do this on purpose. They write it in a generic way because every different set of atoms, you know, are going to slightly behave a little bit differently, and they want flexibility to model that equation with different constants, A, B, M, and N. But they all can be fit with something like this pretty well, okay? This is what's sometimes called the Leonard-Jones potential, right? It's a type of modeling your interaction between atoms, okay? So what does A, B, M, and N typically exist as? What are the numbers they exist as? Let's start with A. A, and it's just a footnote in your book, you might almost miss it, but it tells you that A is equal to Z1, that's the charge of your first ion, times Z2, that's the charge of your second ion, multiplied by the fundamental charge of an electron squared, all divided by 4 times pi times epsilon naught. And I've added what epsilon naught is in our notes from last time. It's the permittivity of free space. It's at 8.85 e to the negative 12 farads per meter. So that's in the notes, okay? So that's A. B is not a typical value. That depends every system, right? M and N are variable. M actually is fixed. It's going to depend on what? M has to be a single value. What about what we learned last time tells us what M is? Maybe turn to a neighbor. How could we guess the value of M? Okay, any thoughts? How could we guess the value of M? Any thoughts? So remember, we've showed you that the force is a function of attractive forces and repulsive forces. Energy is no different. Energy has an attractive term and a repulsive term. And if you take the derivative of that attractive term, we know that R has to be raised to the squared, right? Because that's what physics tells us in terms of attraction, that it's 1 over R squared. So M has to be equal to 1, right? 1 over R, or R to the 1 power. When you take the derivative of that, that's how you get your R squared. So we know that M is going to be equal to 1, okay? And B and N are fitting parameters to make sure that your system fits right. You have a homework problem, you have a couple homework problems where you're going to have to take these derivatives, take the integrals, figure out how to solve for R naught. How do we solve for R naught? You start, let's say I gave you an expression for energy. I told you what A and B are. So you've got this expression, you know what M and N are. If I asked you to tell me, okay, what's the average or the equilibrium bond distance, what would you tell me? How would you solve that? Take the derivative and then what? Set it equal to 0, then what? Solve for R, right? When you take the derivative, that gives you the force expression. When you set it equal to 0, that is the only point. There will only be one point, and when you set that equal to 0, R is R naught. So solve for R, and that's your equilibrium bond separation distance, okay? Which for most materials is something like a few angstroms, a couple angstroms, okay? So that's a 1/10 of a billionth of a meter. So we're talking really, really small distances, okay? Okay, so from these energy potential well diagrams, they actually tell us a ton of interesting things. Let's plot some for different materials, right? So the energy potential well, we call it a potential well because it dips down kind of like a well, right? When we plot energy versus interatomic separation. If we plot it for 3 different materials, say that one versus this one versus this one, right? Those might represent 3 classes of materials. Now, if one's a ceramic, one's a polymer, and one's a metal, how would you guess which one's which? Does this graph tell you anything that might be useful? Ceramic versus polymer versus metal. Here's a tip. Think about the melting point of those 3 different things in general, and then think about how energy might tell you something about melting point. So turn to your neighbor and take a guess. Metal, ceramic, polymer, which one's which? Anybody want to take a guess? How does this relate to melting point? Metal, polymer, ceramic. Who thinks which is which? Anyone want to take a stab at this? Yeah, go ahead. Is it, I forgot your name. Ashton.
The ceramic would be the one that has the shortest, or the highest energy. Most energy.
Uh-huh.
It's the one that has the highest melting point.
Yeah.
The metal and the polymer.
Yeah, that's exactly right. So in that case, the red one would be the ceramic. And the reason why is because from its average bond distance, right, if you're going to melt it, when you melt it, that's basically saying that you can separate the atoms completely, right? That's what happens in a liquid. They're able to freely move from one another. They're not tied to a single other atom. So what that means is you're moving these things infinitely far apart. And in order to do so, you have to overcome the biggest difference in energy. And that's going to come from the thermal energy that's around it, right? So exactly right. And then metals are going to be in between. And polymers will be the lowest. And again, these are all just rules of thumb, and there are exceptions. Like there's really high melting point metals, and there's probably ceramics that melt at low temperatures. Yeah, there are, like water, right? That's a ceramic, and it melts really low, okay? So there's exceptions to these, but in general, these are the rules, okay? What else can we get out of these? We can also get the coefficient of thermal expansion. I'm gonna do a new drawing for this one. Coefficient of thermal expansion, this is pretty cool. Let's draw our potential well again, and let's draw a ceramic. A ceramic looks like this, we said. Now, how can we get coefficient of thermal expansion from this? Any thoughts? So let me ask you this. At 0 Kelvin, you cool this thing all the way down to 0 thermal energy. It's going to sit at the bottom of that well because it has no energy. As you heat it up, you're basically giving that material a little bit of energy. So what it's allowed to do is it's allowed to slosh around a little bit in here, right? It's able to sort of go up and down, which means it's got enough energy at some moment of time to be a little bit closer than it would normally like to be, or a little bit further apart than it would normally like to be, okay? What that does is, the higher and higher temperature we go, we can basically look at what's the average, what's the average distance as you give it more and more thermal energy, right? So let's call these flat lines different temperatures. Higher temperature means it's got more thermal energy. And then plot where the average position is. On average, how separated are these things? So it started out there, it moved to here, moved over a little bit, moved over a little bit, moved over a little bit. So as you heated it up, it's actually doing what? It's expanding, right? Thermal expansion comes from these diagrams. Once you understand these diagrams, not only melting point, but thermal expansion and other stuff can be really easily explained, right? So on average, this thing shifts to the right for almost all materials. It gets larger. There's some materials that actually shifts the other way. You heat them up and they shrink just a little bit. Those are pretty rare. They're interesting materials. They're ceramics. We'll talk more about them later on when we get to thermal properties. The reason why you get a thermal expansion is because this potential well that I've drawn is not symmetric. It's asymmetric, right? One side is a little bit flatter, the other side's a little bit steeper. And that means as you heat it up, the average position scooches over a little bit. Now, the asymmetry of the potential well, you want to write this down. The asymmetry of the potential well, is it 2? I think it's 2. Asymmetry, I don't know if I spelled that right. That just looks wrong. I'm gonna change that. I think that might be better. I don't know. Asymmetry scales with the, is it 2 M's? All right, let's do it right. Something did not look right there. Asymmetry, right? Asymmetry scales with the depth of your potential well. Depth of well. So if you have a material that melts at a higher temperature, it's going to have a deeper potential well. You would expect this thing to have less thermal expansion, right? Less thermal expansion. And this, in fact, is what we see. If you look at typical values of the coefficient of thermal expansion, CTE, so this is your expansion. We'll talk about it later, so I'm not going to go into detail right now. It's just your expansion. It's typically something like less than 10 ppm ppm per K for a ceramic. That means that it's less than 10 parts per million, or 10 e to the negative 6 for a ceramic. So for every degree you heat it up, it's only increasing by 10 parts per million. That's not very much. Whereas metals and polymers can be significantly higher. Metals can be between maybe 10 to 50 or so, and polymers can be over 100, right? Depending on what they are. They can be really big. So polymers, because they have a really low melting point, they have a really shallow potential well, it's very, very asymmetric. So polymers expand like crazy, whereas metals not so much, and ceramics definitely not so much. Okay, any questions on this? How you get melting point, coefficient of thermal expansion? We're going to come back to both of those a little bit later in the semester on thermal properties. The last one I want to introduce is the stiffness, or the Young's modulus. Can I just see raise of hands? Who's heard of Young's modulus before? Should be the vast majority, maybe 3/4 of you. So I'm just going to introduce it briefly. We will come back to this later, so don't worry. This is not the only time we're going to see it. But if you apply a stress to a material, what does the Young's modulus tell you? Stress equals, well, stress over strain equals the Young's modulus. Or in other words, if you bring the strain over here, for a given stress, the Young's modulus tells you how much strain that you achieve in your material. We're going to talk about strain later on. But think of it, a good way to think of Young's modulus right now is the stiffness of a material. So I've got these two atoms that I've got close together. If I pull on them, it might be the case in one material that it's really easy, a small force stretches them quite a bit. But another material that's stiff, a small force doesn't actually make it stretch very much. And these diagrams can tell us that too. Let's go back to our force diagram. Imagine you're at your equilibrium position right here at R0, right? You're right there, and if you apply a force to something, it's going to move. This tells you how much it's going to move, right? If you apply a force equal to that point, you can move it that far away. Fair enough? You can scooch it over just a little bit. So really, Young's modulus from these diagrams can be figured out by taking the slope. The slope at that point is the stiffness of your material. And then if you want the instantaneous stiffness, then you have to keep on taking that slope. But the instantaneous slope, meaning at regular conditions when you first apply your force, that's going to give your stiffness. Mathematically, what that means is this expression. It means that it's equal to the derivative of the force expression with respect to R. So we started with energy. We took the derivative once. That gave us force. Take it again and evaluate that derivative at R equals R0. Multiply that by 1 over R0, and that's a pretty good estimate for stiffness of a material. And I think that's pretty shocking that that actually works. That from basic atomic interactions, we can figure out, we've done 3 wildly different properties. Melting point, how it expands with temperature, and stiffness, right? And there's even more things you can do, but this is all we're going to talk about in this class right now. Any questions before we move on? This is tricky. Yeah, go ahead, Ryan. Yeah, This is 1, so E sub y, great question. That stands for Young's modulus. E is the modulus variable, and they often put a y on it. So again, that's stiffness. That's this guy. So when you apply a stress, let me just actually label these. We will come back to it later. But for a given stress, you will observe a strain. Most of you have seen this already, but for those that haven't, you get, we'll just call it stiffness right now. The stiffness is the constant of proportionality that tells you how much strain you get when you apply a stress to something, and we'll come back. That's equal to 1 over R0, that's your equilibrium bond distance, multiplied by dF dr, that's the derivative of the force expression with respect to R, the interatomic separation, and you're going to evaluate that derivative at R equals R0. That gives you your Young's modulus. It's pretty darn good. It's shocking how good it is. Okay? Okay, we've already talked about that. Already talked about thermal expansion. Should have cut these out of my notes. Okay, something I want to introduce really quickly is the rule of mixtures. You would have seen this before at some point, or you've been doing it in your head without realizing what the name of it was. But the rule of mixtures says the following. If there's a property that you're interested in, let's say density, right? You want to know the density of a composite. And if that composite's made up of 2 things, say like a matrix phase and a fiber phase or a particle phase, if you know the volume fraction of those 2 phases, then you can estimate the property of the composite from the rule of mixtures. We're going to have a whole chapter on composites later on where we go into more detail on this, but for now, we're just going to introduce rule of mixtures because it's useful for a lot of things later this semester. So if you know what the density is of the matrix, and you have the volume fraction of the matrix, and then you add to that the density of, say, the fiber, and you multiply that by the volume fraction of the fiber, then that's a good way to estimate the density of your composite. This works for some things really well. For some things it doesn't work, like stiffness. If you're trying to figure out the stiffness, the Young's modulus of a composite, this actually doesn't work very well. You need to do a modified version of this, which we'll talk about later. But for a lot of things, this works pretty well. I think you need to do this on your first homework. Okay. Because we're a little bit short on time, I'm not going to go into great detail on ionic versus covalent versus van der Waals bonding. I think you should have, everyone had at least first semester of Gen Chem, so you've seen this before. So I'll say that do the reading on it and review it. And the takeaway for me is that it's almost never completely ionic or completely covalent. Very, very rarely. Almost everything has some fraction of ionic character, right? Some percentage ionic, some percent covalent. And we can write this expression as follows, right? The percent ionic character is equal to 1 minus the exponential, ex, right? So this is e, the natural number, of, let's see, negative 1/4 multiplied by the difference in the electronegativity of your two atoms, chi A and chi B. And you're going to square that. Then you multiply this by 100%. Okay? So chi is the electronegativity. There's a table, it's actually a figure in your book that shows you for every element what the electronegativity is, right? Electronegativity, if you recall from Gen Chem, that's the affinity for electrons. You can think of it like it's affinity. How much does it want electrons? Things like fluorine really want that electron. Yeah. So that's E, that's your natural number. So when you have like E raised to the X, this is the same thing as that. When you write out EXP, that's the same as saying like E raised to something. By the way, if you haven't got one of these periodic tables yet, we passed them around. Before the end of class, I think we'll send them around one more time or something. Or you could actually raise your hand real quick. Who doesn't have one of these? There's a lot of people. So we'll send these around and get these to you in a minute. Actually, maybe you can do that now, Danny. These are awesome. This periodic table has a ton of information on it. So this is free. I only have one for each of you, so don't lose it. Hang on to it, right? You'll need these on exams typically. They have a ton of information. For one thing, it shows you like the electronic configuration for everything. It tells you like what of its orbitals are filled. You'll need that for like your first homework. It tells you electronegativity. On the back, it tells you what the common crystal structures are. All sorts of things that we'll use this semester. So hang on to this. I think this is like the best periodic table I've seen. So hang on to it for this class. Okay.
If you didn't grab one, can you raise your hand one more time?
Now, we're just about done with this chapter. Let me just point out that some of the questions here are tricky, and I've done examples. So again, you can either go to Top Hat and follow. So let me show you on Top Hat where it's at again. If you go to chapter 2, on these, you should be able to see these on the worked example problems. You can see these things worked out, or I've embedded them right into our notes right here, and you can just click on the YouTube links for example problems of these types. Okay. So that said, are there any questions before we move on? Okay, let's move to chapter 16. Chapter 16 is all about free energy and electrochemistry, which at first blush, you're like, how are those two related? They're completely related. They're so like one another. You're gonna be shocked by the end of this chapter how similar free energy and electrochemistry are, right? Now that said, the book doesn't have a free energy chapter on it. They just do electrochemistry. So we've provided you some additional readings if that's helpful for you. I'll say that everything you need to know is in these class notes. I'm not going to go into super depth on this. We're just going to introduce concepts, right? And the first concept I want to write out is first off, why do we care about reactions as material scientists? Maybe turn to your neighbor and tell them, why do we care about chemical reactions as engineers in general? Okay, what do we think? Why on earth do we care about, like, if you're a mechanical engineer and you're like, I'm done with chemistry, I never have to do it again. Like, why is that a wrong attitude? Where are you going to run into chemistry despite what you would prefer? Colby, what do you think? Yeah, like, it turns out that we live in a world where materials, like, interact with each other, whether you like it or not. Like, you might design a car and you're like, sweet, it's all mechanics. But like inside that car, you've got all sorts of different materials next to each other, some of them at high temperatures, some of them with like different electronic affinities. Like they're gonna wanna bond with one another, they're gonna wanna react with one another, and they might form other phases. In fact, a lot of you guys, without even liking it, you're gonna have to realize that we actually need to control chemical reactions to get the properties out of things that we want. So I'll give you some examples, right? So you have to care about chemical reactions, even if you're mechanical engineers, I apologize, but I think that you can like it if you learn a little bit about it. So first off, how do you write chemical reactions? You guys have seen this since like high school. It's always like reactants turning into products. What's wrong with this and how we're gonna modify this thought a little bit is that it's actually, everything is about equilibrium. There's always some equilibrium. Even if you take like gasoline, right, and you put it in the piston of your engine and you spark that thing and provide oxygen and you think it's all gonna burn, there's always some equilibrium that doesn't burn or that even goes the other way, right? It goes in reverse. That might be a tiny fraction compared to the amount that goes forward, but we're gonna think of things in terms of equilibrium this chapter, right? And then the other thing is that a lot of the equations that you might not have seen before involve the transfer of an electron, right? You start out with a species, but in order for the reaction to take place, there has to be an exchange of electrons. We can see examples of that all around us. So first off, we call them oxidation reduction reactions, right? So oxidation is the loss of an electron, whereas reduction is the gain of an electron. So the oxidized species is the one that's losing its electrons. Let's say you started out with iron and it turned into iron 2+, it was oxidized. Whereas if you had zinc 2+ ions and they plate into zinc metal, it had to pick up 2 electrons to do that, so it was reduced. Where do we care about this? How about the batteries in your phone? Every one of you has probably a lithium ion polymer battery in your phone. Inside that reaction, we could write the reaction like this. It looks like the following. Oh, not for water electrolysis, we're gonna do batteries instead. So inside of your battery, you've got lithium cobaltate. So this is an oxide of lithium and cobalt together. You've got 6 graphite, and then that's going to have a chemical reaction between the lithium reacting with the graphite and you ending up with just cobalt oxide, CO2O4. So let me ask you this, turn to a neighbor and tell them, where's the electron exchange happening here? Is there an electron exchange? It's a battery, so there better be. Where's it at? To make it a little easier, I've split the overall reaction into what are called the 2 half-cell reactions. Whenever you hear some people talk about a half-cell reaction, they're talking about the oxidation reaction and the reduction reaction. Oxidation is one that's losing its electrons, reduction is one that's gaining them. So what's happening? Anybody identify the species that are changing their oxidation state? What is the oxidation state? That's like the plus 1 on lithium. There's oxygen, which is -2. We remember from their periodic table what we learned about it. It's right here, and so it wants to pick up 2 more to become like neon. So what's changing its oxidation state in these reactions? Cobalt is. What does cobalt start out as? Well, you've got 4 oxygens, and they're each -2. So overall in that compound, you have a -8 charge, and you've got 1 lithium. So you have to have your positives and your negative equal each other. That's electron neutrality. Compounds are almost never stable if they're not balanced electroneutrality, right? So overall, we have to end up with a +7 between 2 cobalts. That means on average, cobalt has a positive 3.5 charge, right? Now, how do you have a half of an electron? 3 1/2 electrons? You don't. What that really means is that you have 1 cobalt 3+, 1 cobalt 4+, and you have equal numbers, right? But take a look at this one over here. What's happened in that one? In cobalt 204, what's your charge of your cobalt? Yeah, it's +4. Both of them are just +4. So cobalt has lost or picked up an electron. There was 2 cobalts before. One was 3+, one was 4+. Now there's 2 cobalts. One is 4+, one is 4+. So on average, you've lost 1 electron for that reaction. if you lost an electron, that was your oxidation, right? That was oxidized the way I've written it. Meanwhile, take a look over here. Carbon, pure graphite, has a charge of 0. It's electrically neutral, right? But when it picks up this lithium, which is positive 1, on average, over 6 carbons, there's a -1 charge. So it's gained an electron. That's a reduction reaction, right? So you've got your oxidation and your reduction, okay? So we're going to come back to more of these later on. But every electrochemical reaction, whether it's the lithium cobaltate battery that you've got in your phone right now, in your laptop, they can always be split up into oxidation and reduction. And we're going to talk more about them later. But first, let's move to, and by the way, and if you haven't balanced equations before, you should have in Gen Chem. But if you need a refresher, these are here. And I suggest actually coming with these to TA hours and working through them if you need a refresher. Some of these are tricky, actually, to balance. This is like gasoline burning with oxygen to form like gaseous products in your engine. Okay, now the question is this, okay? How on earth, for any given reaction, how do you know which way is gonna go forward? Is it spontaneous as you've written it? Or do you need to reverse the products and the reactants, and is that one spontaneous? So turn to a neighbor and tell me, how on earth do we know which one's favorable? Okay, what do we think? How do we know whether a reaction goes forward or not? Because I can come up with any reaction I want in my brain. I could say, okay, how about this one? A diamond ring, that's carbon. Diamond plus oxygen, maybe it reacts to form carbon dioxide, right? How do I know if that reaction happens or not? For one thing, we might have some physical intuition where we've seen it, right? You know that diamond doesn't turn into graphite, or it doesn't combust with oxygen to form CO2. What else can we do though? Is there a better way to do this than just trying to physically observe all these things? What do we do? Anybody? Bueller? Yeah, what do you think? Bingo. Everything in this entire class. You guys didn't know the answer? You forgot the tip I gave you from yesterday. Does it lower the energy? That's the answer, right? That's how you know whether anything happens. You lower the energy, right? Does energy go down? Right? Is it in a lower energy state afterwards than before? Then it's spontaneous. It's going to happen. Doesn't necessarily mean it's going to happen fast. Kinetics answers that question. But thermodynamically, we know that it's favorable if it goes down in energy. So thermodynamics, I don't think you woke up this morning and thought to yourself, I think I'm going to learn about the first law of thermodynamics today. Probably the second one too, but here we are, doing it anyways. What is thermodynamics? Thermodynamics is the study of heat as it relates to energy and work, right? That's thermodynamics, hence the name thermo, right? Thermodynamics. And it is what we use to predict whether reactions happen or not, okay? Now, to do thermodynamics, we have to introduce some variables that we're going to be using throughout all the semester. T, that's our temperature. It's going to be constant throughout all the system if we're in thermal equilibrium. So we're going to make a bunch of assumptions this semester that make thermo really easy. When you take thermo, it will be harder, but this is like easy thermo right now, okay? There's P, which is pressure. And again, if the system's in mechanical equilibrium, we're going to say that that is constant throughout. There's also mass, there's volume, and now we get to the first tricky one, internal energy. Internal energy, that's like the total amount of energy that's stored in that thing. That's like your chemical bonds. That's all the energy that is feasibly in there. And it turns out that we don't have a really easy way of measuring internal energy. It's really hard for us to measure energy. Because think about it. Every one of us has like in our bodies like a million different chemicals, billions of chemicals, right? All doing things. And then we all are maybe like moving in a car, and that's like kinetic energy that we have. Plus we're on this planet that's like swinging around the sun. So it's really, really hard to nail down exactly what our total energy is, exact energy is at any given moment. So instead what we're going to do is we're going to talk about differences in energy. That's much easier to do, okay? So first let's start with internal energy. What is internal energy equal to? Here comes the first law of thermodynamics. It is the following. The total change in internal energy is heat added to the system minus work done on the surroundings. So I'm gonna say that since it's the change in internal energy, du is equal to dq, that's our change in heat, that's heat going in or out of our system, plus, or minus, sorry, P dV. So at a given pressure, let's say your system expands, then there's a change in volume. It's doing work on its surroundings by expanding. Like when you blow up a balloon, I'm actually doing work on the air in this room because I'm expanding that balloon, right? So that's work. So heat and work. Okay. Oops. So it's helpful for us to define another variable now, which is enthalpy. Enthalpy says that it is a measure of the total energy of a thermodynamic system. H is equal to our internal energy plus P times V. So whatever your internal energy is, if you add the work that it's doing on its surroundings, that's the total energy. So this is H, or enthalpy. And now, catch this. What about the change in enthalpy? dH. If we take this derivative, we've got du, right? Plus, we have to do the chain rule here. We're going to do P dV plus V dP, right? When you take a derivative and it's got the two variables, since we're taking the derivative with respect to all these variables, what is the change in the enthalpy? That's the change in enthalpy. But it also starts to get easier, because what if you do this at constant pressure? Like, let's say I've got a reaction happening here on my desktop, and it's at constant 1 atmosphere of pressure. It's not in like a pressurized vessel or anything. Then dP, this thing goes to 0 if constant pressure. If constant pressure. And if I got bad handwriting, just let me know if you can't read something and I'll rewrite it or say what it is. But that says if constant pressure, okay? And then all of a sudden, this gets easy because this right here, du plus pdv, well, that's just equal to, what is that, like negative q? That's dq. Oh, that is dq, sorry. That right there is dq from this guy. If we solve for dq, that's it right there. So think about what this says. For reactions that happen with no change in atmospheric pressure, right? So pressure is constant. The change in enthalpy is just equal to the change in heat. Change in heat is something that we can measure pretty easily. Like, we've got tools, we've got thermocouples, thermometers, right? We can measure heat change with at least some degree of ability, right? So we can measure enthalpy, okay? What does that do for us, right? Okay, first off, if it gives off heat, we call that exothermic. That means that dq is positive, right? Exothermic means that heat is released. If it absorbs heat, then it's endothermic, and that means it's getting colder, basically. It has to absorb heat, so it's getting colder, right? You've seen or heard of these before, exothermic versus endothermic. That's our first thing that we're going to learn from enthalpy here. Now, enthalpies are additive and reversible, and I'm going to talk more about that in a moment. Let me ask you this. Just based off of what you've experienced, which one's favorable? Exothermic reactions, where heat is generated, or endothermic reactions where heat needs to be pulled into the system? Which one's favorable?
Doesn't it depend?
What's that?
Doesn't it depend on how you're using it?
You betcha it depends. It depends is the absolutely best answer, but generally speaking, which one's favorable? Exothermic is spontaneous, meaning it's favorable. Well, favorable meaning it's spontaneous. It happens on its own. That's not always the case, but it's usually the case that something that gives off heat is favorable. For example, I've got carbon dioxide and air, like water vapor, in this room. So it would be endothermic for me to combine those two things to create oxygen gas and gasoline. Is it happening in this room? Like, there is some equilibrium constant. I'm sure it's tiny. Like, I don't know if it's even measurable, but that is technically feasible, and it's probably in some tiny degree, but it's not spontaneous. It's not favorable. The favorable reaction is one that goes the other way. You burn gasoline, you create a ton of heat, and you get these products, okay? That's enthalpy. That's the first thing that we need to know about. The only thing that we're going to use thermal in this class, we need to get to two things. Three things, really, but one is based on. You need entropy, enthalpy, and then total energy term. So we've done enthalpy already, and it's just heat. Heat in or heat out, right? Because we've made a lot of assumptions so far. Next up, let's talk about entropy. Entropy is the number of specific ways in which a system can be arranged. This is a little tricky. Entropy is really, I think, the better way for us to think about it in this class. It's the degree, if you could sort of like put a number to it, to the degree of disorder of a system, that's entropy, right? So for example, if all the seats in this room were empty, and you guys are atoms, right? And I introduce one atom, then that atom can sit in any one of these seats. And if there's like 150 seats in here, then there's 150 configurations, right? 150 ways that I can place that one atom in here. But what happens if I've got 2 students? If I've got 2 students, there's like 149 that I can just, if I leave like Sarai here and I move Danny around, then there's 149 configurations. But then I can do more. I can say, now Sarai's going to sit right here, and I'm going to move Danny everywhere. And we could go through the entire thing like that. And we went from 150 configurations to like a humongous number, right? And so if you tried to actually calculate what's the maximum disorder, the ways that I could arrange atoms in this room, it would be to have 50% students in here and 50% seats, right? That would maximize our entropy, right? Think of it this way. Let's say I've got a bucket full of white marbles, and then I've got a bucket full of red marbles, right? And if I pour some of the red marbles into the white bucket, those things could go in all sorts of different places. So I've increased the disorder of that system. The entropy has gone up. In fact, if you had an equal mixture of those things, let me ask you this. If I ever half fill a bucket with white marbles, and then I half fill it with red marbles on top of that, I shake it up so they can move around a little bit, will it ever happen that they will recombine and stay like white and red, or will they mix? Why on earth do they mix? Why do they mix? It will never happen. Like statistically, there's like a probability, but it's like vanishingly small, right? Why? Why is it so much more favorable for things to mix in the back?
There's just like a lot more different variations that they're mixed together, and there's only one variation where they're separated.
Yeah, that's a great way to think of it. There's like billions of combinations that are feasible where they're not mixed, and only one where they are mixed. And you're going to give it thermal energy that things can move around. The odds of it mixing is just higher. You just stated the second law of thermodynamics. Congratulations. Well done. Right? So that's the two we're going to use. First and second law. The first one said that the change in enthalpy is equal to heat if the pressure stays constant. Right? The second one is that entropy tends to increase. The change in entropy overall in a system doesn't go down. Right? You can make things order, but it costs energy. So we're going to join those two in a minute. But first I have a clicker example for us, right? So we're going to watch a video here. If I can find it. Nope. Under downloads. So we've got this. This is a rubber band. Okay. I'm super disappointed in myself. Okay. I'm going to start this quiz right now. So the quiz is as follows, okay? You should be able to answer this first one. The first question says, oh gosh. Can you read that? On your thing, maybe you can read it. But it says the following. Is a rubber band contraction reaction exothermic or endothermic? So we need somebody to help us out with this. So Spencer, can I ask you to do something? I want you to hold this out like this, and then next to like your forehead or your nose or something. Yeah, that would be good. Why don't you present it to other people? Take that thing, stretch it out, and let it equilibrate the temperature, and then let it relax and tell us what you feel. Well, you gotta hold it against like your face. Let it move. And maybe don't touch your face just because then it's like getting in the body temperature. So hold it right there. Shrink it and touch it. It was a little bit slower than I liked, but
You want a different example? I'm not a very good one.
well, here's a good rule for science. Like you average data, so we're gonna get more data points. Barrett and Jack. And one more. Don't tell me. It's from, I have funny mnemonic devices. I don't remember who this is. It's the guy from Terminator. The kid from Terminator. What's his name? Connor. Connor! It's Connor! Connor. Okay, all of you guys, stretch it out, but don't touch your face with it yet. Let it equilibrate. Let it shrink and then feel it. All right, what do you think? Hot or colder? Colder. Colder. Cold. Cold. I don't know if I believe that. I don't know. Colder? Okay, it's colder. We believe that it got colder. So was that reaction exothermic or endothermic? Go ahead and get your answers in. Okay, get your answers in. Okay, get your answers in. We're going to pause this one. Endothermic or exothermic? It got colder. You guys should do this one just fine. 5 people, and I just don't want to click it because it's such an easy one. We're going to do it. It's over. It's over. Okay, correct answer is exothermic, right? Majority of people, 3/4 got that right. It got colder, therefore it must have absorbed energy. That's an endothermic reaction, okay? Let's go to our next one. Check this one out, okay? Okay, the rubber band contraction, when you start out stretched and then you contract, that's the reaction we're talking about. I could write like this in reaction form, stretched versus contracted, right? Is that spontaneous, true or false? Okay, true or false, is that spontaneous? Spontaneous just means it happens on its own. You don't have to drive it with force or work. Okay, I'm going to end this poll. Get your answers in. Okay. Is that spontaneous? This better be... Come on. It happens automatically. Like, it's stretched. Like, you let it go. It contracts, right? That's spontaneous. Okay? Let's keep going. By the way, all of these, half your points are just for clicking something. The other half is for getting it right. Right? Let's go to our next one. This one's trickier. For an endothermic reaction, are bonds formed or broken? This one's harder. Endothermic reaction, it's going to absorb energy. Are you breaking bonds or are you forming bonds? Okay, go ahead, get your answers in. Okay, we're going to end this one. Is it broken or formed bonds? I think we're going to get a split on here. It's actually wrong. The majority are wrong here. It's actually when you break bonds. Think of it like this. If these two are bonded, these are two atoms, and I'm going to break this bond, I've got to overcome that potential energy well. That's going to take energy. They're going to absorb energy, and I'm going to pull them apart from them. That's breaking bonds. So that's endothermic. Okay, let's go to our next one. I promise this is all tying together. Give it just one more minute. Okay, as the band is stretched, so when you stretch the rubber band out, when we release that thing, that's endothermic. We just proved it because it got cold. And I just told you when things when they're endothermic, when they get cold, that means that we're breaking bonds. So the question is, when you got this thing, that means that in this state where it's stretched out, there are bonds formed, and when we release it, we're breaking those bonds. So the question is, what type of bonds are we talking about? Are these covalent, ionic, van der Waals, or metallic? What bonds am I breaking when I go from like this to like that? I just broke a bunch of bonds. What were they? Every time I do this, I have to like
Which way are you going?
make sure I have the right answer. Okay, get your answers in. A, B, C, or D. I'm going to end the poll. Okay, what do you think? They are, in fact, van der Waals bonds. If you remember from chemistry, first off, what is an elastic? What is a polymer? A polymer is a bunch of spaghetti noodles. Like imagine like a pasta bowl. If I tried to grab a single like pasta noodle and pull it out of like the pasta bowl, it's just going to slide mostly past those things, but it might get entangled a little bit. That's kind of what's happening with elastics. Instead of just regular pasta, imagine you have like boiled spaghetti noodles, and then you drizzled like super glue over it, just like like a vinaigrette of super glue, right? Now when you pull on that, it's gonna like, they're stuck together, but only at certain spots. We call that cross-linking. We're gonna learn way more about it later on. But if I pull on it, it makes the whole thing sort of stretch. So when you do that, the thing that's resisting me pulling it right now is those cross-links. And I've lined up a bunch of polymer chains, right? They were like spaghetti, but if I pull on that thing, on average, they start to line up with one another. I know we're just out of time. They start to line up with each other. But as they do line up with each other, they form van der Waals bonds between the strands of spaghetti. So the last question that we're going to do is I'm going to ask the following. If I take a rubber band and I hang it, right, like I put a weight on the end, I leave it like this, and then I blow this thing with a blow dryer, and I used to do this, but then I broke my wife's blow dryer and she banished me from using it. So now we're going to watch a video, right? But what will happen, so bear with me, I know we're like 1 minute over, but bear with me. So this thing is hanging, they haven't started blow drying it yet. They're going to start in just a moment. You can see that it's hanging, it's at like 18 on that ruler. What's going to happen as they blow dry it? Any minute now. Okay, they're blow drying it. It's shrinking, right? So that's when you heat it, right? I forgot to even like hit play on this, so now you know the answer. So get your free point, but like next class, so go ahead. If it's stretched out, you hang a weight, you blow dry it, will it expand, contract, or nothing? You now know that it's going to contract. When we start class next time, you will all teach me why on earth it's doing that using entropy and enthalpy arguments. What's up? What's that? Can I explain them? Yeah, so van der Waals bonds, they come about so let's say you've got, let me turn that off. Sorry, let me save this real quick.